Now comes the fun part. There is a very, very popular, fairly widely used test called permutation testing, also called as permutation resampling test. These are the steps that are there in this. First, let's see. Okay, let's understand this and then we'll ask counter questions and all that. Okay, so what does this test do? This is again one of the very simple, very powerful, very easy to understand tests, also widely used in a lot of real situations. So what we do is this. So let's try to stack up all of our data. We have n observations. This sea blue or sea green color is all of our observations from the control. This is time spent by customers or users in the control group. This is time spent by users in the treatment group. N observations here, n observations here. We combine them first. Okay. Again, this is a bunch of numbers. This is a bunch of numbers. We combine them. Then we shuffle these. Look at this. When I say shuffle, we will mix all of them. Think about a simple analogy I can give you for mixing. The physical analogy is take a bowl, right? Put all the customers from the control group and the treatment group, shuffle the whole thing, right? So exactly that's what we are doing here. So each of these is an observation. We have concatenated these two lists, if you think about them as lists or arrays, right? And then we are shuffling everything. So they'll be randomly shuffled. The shuffling is also called as permuting. What is permuting? Probably you learned in your 11th and 12th class math, right? So imagine if I have some 4 numbers. What is a permutation? If I want to permute these, what is a permutation of these numbers? 3, 4, 1, 2. This is one permutation of these numbers, right? Also called as a shuffle, right? So all that we are doing here is we are taking these numbers and we are randomly shuffling them. The shuffle or permuting has to be random. Now, what is the length of this list or array now? This length or list is n plus m elements, right? Completely. Now, I don't care. Again, remember, these are numbers, right? This is maybe 10 minutes. This is 20 minutes. This is 30 minutes. These are just basically numbers. I've color coded them to show that we are shuffling. But after we shuffle, we don't know which is what. That's the fun part, right? Now, after we shuffle, remember, we have an array now of n plus m observations. We break this whole array into 2 sub-arrays now. This is called splitting, also called as sampling or resampling. This is called splitting or sampling. So we take this whole n plus m. Again, this is randomly shuffled. We take the first n elements and create a set called S1. Take the next m elements after shuffling or permuting or rearranging, right? This is called S1 dash. Okay, look at this. Permuting, this is called splitting or resampling or sampling. It's often referred to as resampling. That's why this test is called permutation resampling test. Okay, so after doing that, I'm going to say, hey, let's take the median of all these S1 values. Take the median of S1 dash values. Let's compute the difference. Okay, so median of S1 dash. Okay, so again, because this is treatment, right? Again, remember the treatment is m elements, the control is n elements. So we are taking the median of S1 dash minus median of S1. So again, what we got here is, let's just call it median difference 1. Okay, because this is split 1. Remember, look at the steps. In permutation testing, you combine the data, you permute, rearrange, or reshuffle, and then you resample the data. You break it down into this. You break it down into 2 parts, compute the difference between medians. Now, what you got is a median difference 1. The game is not yet over. We are just getting started. Again, this is probably one of the most important and interesting ideas in probability. It might take a little time to digest, so that's why I'm going to go a little slowly here. Now, your question should be, always ask why. That's very important. Now, you might say, why the heck are we combining shuffling and splitting? Or why are we combining permuting and resampling? Why are we doing this whole headache? Now, remember, what we want to say, this is probably one of the most important ideas here in the whole permutation resampling test. We understood how it is done. See, till now, what I've explained here is how it is done. But why it is done is also very important. So let's try to understand that. So imagine your control and treatment are not different at all. Let's assume your control is same, very similar to your treatment, very similar, or that's why I'm putting this to say that they're very similar, if not exactly same, or they could even be exactly same. If they are very similar, right? What do we mean when we say they're similar? Which means they're coming from the same population. Again, remember, I hope you understand this terminology, right? Population is all the data that's available. But since we don't have access to all the data, we have only some customers' data, right? Population is the millions of customers that are there. So we have some sample here and some sample here. Now, if both of them are similar, then if let's write that big if, there's a big if, so let me highlight it here. If both of them are same, then if I take the union of both these, they're observations, right? At the end of the day, a bunch of observations. There's also a bunch of observations. If I combine, by combining, what are we doing? We're taking a union, or we're just combining them literally, right? By combining them, I'm combining these observations and these observations, and now I'm saying, imagine if there is no difference between xc and xt, which means they come from the same distribution. Let's say there is no difference between the distributions. Then, if I shuffle all of them, here comes the fun part. This is probably the trickiest part to digest. Now, by combining them and shuffling them, I'm mixing all these values, right? This is actual data. Let's not forget that. And this is the only data that we have, these n plus m observations. Now, by mixing all of them and then randomly splitting this into a group of n and m elements, I am saying, in a world, let's take a hypothetical world where xc is very similar to xt, right? By combining everything and then resampling, again resampling m and n samples of size n and m. What did we call these? We called them as S1 and S1 dash. We called it as set 1 and set 1 dash. Imagine if both of them are the same and we sampled n elements and m elements here. What would be the difference between these means? Again, these medians. The diff in median will still exist. It will never be zero in the reality. The difference in medians, even if both of them are come from the same distribution, there will still be some difference in median, because these are n samples and m samples, right? Even if xc and xt are exactly the same distribution, by combining everything and resampling, I'm saying, what if all of this, what if xc and xt are the same distribution and I sample n elements here, m elements here? The difference in means between, the difference in medians, there will be some, this value very often could be zero, but it will also differ from zero in some instances. So what we're trying to do here is, this is the most important part. By combining, shuffling, and splitting, what we're trying to say here is, we are trying to simulate, this is a simulation. If control and treatment data come from the same distribution, then what would be the types of values that we will observe for differences in means? If they come from the same distribution, if they come, they may not come, that will have to negate. Again, this similar experiment can be done not just for medians, but for any metric. Okay. So remember that the median difference one. Now, what is median difference one here? Median difference one is after combining, shuffling, after splitting. Again, this is only one split, right? I took the difference between the medians of treatment, and this is not treatment. This is basically m samples and n samples, right? So median diff 1 is one possible value of median diff. Remember, median diff is also a random variable. It's also a random variable. So it is one possible value of median difference if control and treatment are the same with no difference. So if xc is very similar to xt, median diff is one possible value of the difference between medians. That's what I just told you a while ago. Now, what we'll do here is, because we have a computer at our hand, right? We will just repeat this k number of times. Every time you get, first time you get median diff 1, second time we get median diff 2, third time we get median diff k. You get k such medians. We'll just call them as median differences. We'll just call them as m1, m2, mk. Remember, what do we have now? Through permutations and resampling, k times, we have produced k possible values of these median differences. These are k possible values if xc is very similar to xt. But we also have an observed difference. Let's not forget that. This is the observed difference. This is the difference between the median of the median value of xt and the median value of xc. Okay, so median difference observed. Let me just take you back there. So that median difference observed is this. And we said, let's assume it's some 20, let's just assume it's 20 minutes. So we are just going to call it as median observed. Again, every time instead of writing median diff something, I'll just write it as M1, M2, Mk. These are the differences of medians that we have observed in our permutation and resampling, assuming that xc is same as xt. While this is the actual observed in our control treatment. This is what we observed in our control treatment. Now comes the fun part. Now let's plot. Imagine we try to plot the PDF of these M values. So we got M1, M2, so on and so forth. We got some MK values, right? Again, what are these MK values? These are the differences in medians, assuming XT is same as XT. Let's not forget that. These are median differences, assuming this. We simulated this setup. Now, if I plot the distribution, very often this value will be close to 0, right? Because imagine if XC and XT have the same distribution, right? Very simple logic. If XC has the same distribution as XT, then if I take some N samples and I take M samples, I compute the median here, I compute the median. The difference between these medians, which we just computed, most of those differences will be close to 0. Some could be negative, some could be positive, right? So this is the PDF of this M, which is basically we are taking these K values and we are plotting the PDF. Now comes the fun part. Now we say, these are the values that we typically observe. Remember, these are the differences of medians that we typically observe if XT and XC are the same. Given that, what is the actual observed value that we observed right now? From our control treatment. Remember, from our control treatment, what did we observe? We observed, let's say, 20 minutes of difference. Now your question should be, typically, we should observe the data to be coming from this sort of distribution. But what we observed is this. Now is the fun part. What is the probability? Let's compute this now, right? Let's compute this. What is, again, I'm just plotting the data here, nothing else. Okay, we have not come to any conclusions. Now, our question is this. What is the probability of observing a median difference of greater than equal to 20? This is the observed. This is the median difference which is observed. What is the probability of observing a median difference of greater than 20, which was the actual observed between control and treatment? Conditioned on, this is conditional probability, right? You probably learned it in your 11th and 12th class or your undergraduate days. Conditioned on the fact that there is no difference between control and treatment. Look at this. So this is same as saying your XC is very similar to XC. This is a probability. Now, how do we obtain that probability? Let's try to understand. What are we saying? We are saying, what is the probability of observing a median difference of 20 or more, or as extreme as 20 or more extreme than 20, given that my control and treatment are similar? Let's assume, how do I compute this value now? If you think about it, I will simply say, this is my PDF, right? This is my PDF. I will simply say, take the area under this curve. There is a curve here, right? There is this orange curve here. Okay, let me draw that orange curve clearly here. There is an orange curve here. I'll take the area under the curve. What does this area tell me? What is a PDF's area here tell me? This says, what is the probability that this M, this random variable M, which is a random variable of median differences, is greater than equal to 20? And how is this M itself generated? This M itself is generated assuming that XC is very similar to XT, right? So in other words, if you think more mathematically, the question, the conditional probability that we're trying to compute is what is the probability of observing a median difference as extreme as what we observed in our control treatment. This is what we observed in our control treatment, a value of 20. What is the probability of observing a median difference, assuming that XC and XT are different, or sorry, are same, I'm sorry. Suppose you computed the area under the curve and that turns out to be 0.02, okay, 2%. Now your question is this. Let's write this probability again, okay. Now, again, for those of you who may have forgotten, the total area under this whole curve is 1. Okay, in case you have forgotten that from your basic 11th and 12th class probability. Okay, so what we got as this observed value is 2%. Now let's think about it. Let's take a step back and think again. Suppose you are living in a world where there is actually no difference between control and treatment. There is no difference. Your XC is very similar to XT. Let's assume this is a world that we live in. Let's just assume this is true. This is true in a given world. In that world, what is the problem? Again, in this world, we already observed this 20. Let's not forget that. We already observed this in our A/B test or in our control treatment test. In this world, what is the probability that M, right, which is a median difference, is greater than 20? It's actually very small. It's just 2%. If this was true, look at this. If this was true, the probability of observing something like this is very, very small, right? Which means, but remember, we already observed this value of 20. Remember, we already observed this value of 20. We started off here, right? This is empirical observation from our data. We observed this already. We can't say our observation is incorrect. Your observation is truth, right? Now your question that you have to ask yourself is this. In a world where there is no difference between control and treatment, which means XC and XT are the same, the probability of observing something that we observed is very small, which means here comes the great idea, which implies that this world where XC is very similar to XT is not likely to be true. Look at this. Look at the idea. Again, I'll repeat this. This is very, very important step. The probability of observing a median difference greater than 20 that we actually observed under this assumption is very small, which means if you take a world where XC and XT are the same, in this world, the probability of observing 20, which is our observed value, which we already observed, which is true. Your observation can't be false. Your observation is true. Now, you're saying if this worldview is true, then the probability of observing what I've observed is very, 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 very small. The probability is very small, which means this worldview must be unlikely. You're not saying it's always untrue. Remember, suppose if you have this probability of observing M greater than equal to M observed, what is M observed now? 20. If this is equal to 2%, you are saying, okay, so let me also write this. Let me write the full statement. Okay, assuming XC is similar to XT is 2%, which means, again, this is very important. This is a very typical fallacy that people commit. In a world where XC and XT are the same, there is still 2% probability that you may observe a value that is as extreme as 20 or more. There is still some probability. It's not zero probability. Okay, there is still 2% probability. It's not 0%, but 2% is very small. Okay, that's the idea here. So now what we'll say here is that this world is less likely to be true because this probability is so small. So we will conclude that there is some difference in the medians of XC and XT. This is the conclusion. We are only saying that they're not same. There is some difference. They're not one and the same. And of course, your empirical data saying that because what have you observed here? Your observation is that the median of your observation is the median of XT minus the median of XC. This is what you're saying, right? This value, your observed value is 20. right? And such an extreme value is very, very less likely if xt and xc were the same. So you would say xc is not similar to xt. First, this is, again, you're giving, again, there is a possibility. There is a possibility that they may be same. That possibility is only 2%. There is a possibility. We are not saying there is a 0% probability that they are the same. Given what we have observed, given that we have observed 20, there is a small probability that xc and xt are still same, but that probability is very low.